Welcome to lecture 27 on the proof complexity as a computational lens course. Today we're going to talk about automatability. Going back to the computational lens where we started. So what do we want from a proof system if we want to use it to actually solve problems? So desirable properties of a proof system fancy style P under consideration. So we would like it to have reasoning power. So we would like it to be powerful, but so that there are short proofs. But then algorithmically, it would be nice to actually be able to find these proofs. So we also want the proof system to admit efficient proof search. So this is the question we're interested in today. And we have to start discussing what we mean by efficient proof search. We know what efficient means. I mean, running in polynomial time. So basically, efficient proof search is, in our proof system P, we want to find some refutation of the input formula F efficiently. Now, the point is that what is efficient? Well, if the proof system cannot refute F efficiently, if the proof system requires exponential size to refute F, then clearly we cannot expect to find a proof that is more efficient than that. So it's reasonable to say that we're measuring efficiency in terms of best possible output. So we should really measure performance in terms of best possible S refutation of F in the proof system P. But now you realize there's also like another stupid case. Suppose that F is this formula that contains a lot of junk, and then somewhere at the end or in the middle, I don't know, you suddenly see a variable appearing both positive and negative. Now, obviously, the best refutation of this will just resolve in resolution, say, x and not x, and the proof will have constant size, and polynomial in a constant is a constant, which doesn't even give us time to parse the input. So we want to have time to read the formula, so the right notion is to say, let me get time to read the formula and then to find the best possible proof there is. So we'll say that the proof system P is automatable if there exists some algorithm, let me call it S for proof search algorithm, that runs in time this on, so polynomial in the size of the smallest proof plus the size of the formula itself. In time poly in this, and on input F, it outputs some P refutation of F. Not necessarily the shortest one at all, but it will be reasonably short. I mean, if we're running in polynomial time measured in the size of the smallest proof, then in particular, that's an upper bound on the proof size. So this notion of automatability is from Bonnet, Pitassi, and Rouse. Where you have to be, but you have to be a little bit careful to not just get polynomial time in the proof, but also in the formula. And now you can also study notions of, so this is polynomial automatability. This is the most efficient type. You could say, I mean, you could relax your condition. Maybe you want to be just quasi-polynomial in this or sub-exponential in this, and then you can define notions of being automatable in quasi-polynomial time or sub-exponential time or something like this. Okay, so today this is what we want to talk about. So one somewhat related notion. Oh, let me just say one thing. I like throughout today, unless I mention otherwise, n is going to be the number of variables in this input formula f, which we're assuming to be unsatisfiable most of the time, unless stated otherwise, and we want to find the refutation of. So we know that if f has a resolution, Nullstellensatz, or polynomial calculus refutation in width or degree d, then we can find a refutation in time n to the d. In time and in size n to the big O of d. And this is sort of some kind of we could call it width automatability or degree automatability for the algebraic proof systems. So this is getting us close to what we want, but not quite. Why? Well, because we know that there are formulas that have for resolution and polynomial calculus, there are formulas with which require square root n width or degree and still have very short proofs. And for Nordström, it's even worse. There are formulas with extremely short proofs that require degree n over log n. Okay, so all of these three proof systems are what we can call width or degree automatable, but that is not what we're looking for. So what is known about this? So the first really significant result, I would say, maybe for these proof systems, is by Alekhnovich and Razborov. Okay, one thing we can note is, so in particular, I mean, we're doing lower bounds, so where are we going? We might suspect that interesting proof systems don't have this property. That's where we're going. Then obviously we need to assume something. It's not so hard to show, but maybe I'll leave this as an exercise. If P is equal to NP, then these proof systems, pretty much any proof system you can think of, I think, is automatable if P is equal to NP. So a necessary condition for not being automatable is P distinct from NP. So that would be like if we want to prove non-automatability, then the best we can hope for is a result saying like, if P is distinct from NP, then efficient proof search is impossible. But we can also think about throwing in stronger assumptions than just P distinct from NP. So Alekhnovich and Razborov proved that resolution is not automatizable unless, and I won't go into the exact assumption, but basically there is in parameterized complexity theory, there is a hierarchy which I guess people believe that this hierarchy, that this is a strict hierarchy. And what Alekhnovich and Razborov proved that, well, suppose that resolution is automatizable, then that this hierarchy collapses, which we don't believe. And then Galesi and Lauria later proved the same thing for polynomial calculus. And it doesn't really matter, they get it for polynomial calculus, also for polynomial calculus with dual variables, so this with twin variables, PCR. Okay? So for stronger proof systems, we can say, we can have the notion that a proof system is, let's say that it's weakly automatable. Proof system is weakly automatable if it's polynomially simulated by an automatable proof system. Let's call this proof system Q, maybe. So we might not be able to search for P proofs efficiently, but if there is a short P proof, then some other proof system Q, which is at least as strong as P, we can search for Q proofs efficiently. And you can argue that for algorithmic purposes, this is also pretty good. This is the notion of weak automatability. So now, if the proof system P is closed under restrictions, which most proof systems are, that we've thought about, what we mean by this, like if I take a proof refuting a formula F, if I hit the formula and the proof with the restriction rho, then the proof restricted by rho is a proof of unsatisfiability of the formula F restricted by rho. Not all proof systems have this property. In particular, proof systems that closely model SAT solvers, for instance, typically do not have this property, which is very annoying. But as we've argued, resolution, Nullstellensatz, polynomial calculus, cutting planes have this property. So for any proof system that is well behaved in this sense, it holds that if you're weakly automatable, weak automatability implies feasible interpolation. So any proof system, if it is weakly automatable, which we may or may not believe, probably not believe, then this implies that the proof system has feasible interpolation. And if P is strong enough, think Frege extended Frege, the converse also holds. So it's an equivalence. If a proof system is strong enough, then it's weakly automatable if and only if it admits feasible interpolation. And now the point is that under cryptographic assumptions, so much stronger assumptions than P distinct from NP, under cryptographic assumptions, we have that bounded depth Frege, Frege and extended Frege, which we talked about in the very first lecture. It's not so important what these details are, but they are, if you believe that there is safe cryptography, basically, then these proof systems are, they do not have feasible interpolation. Okay, so strong enough proof system, if you believe in cryptography, they do not admit efficient proof search. So now the question becomes, it sort of tells you it's a no free lunch theorem, if you like. I mean, Frege and extended Frege are amazing proof systems. We know that they can prove, in fact, I mean, we have no really good candidates for lower bounding formulas even for these proof systems, except for random KCNFs. But unfortunately, we also don't expect to be able to search for proofs efficiently. So now the question is, we can ask more about, okay, what about weaker proof systems, like resolution, like Nordström, like polynomial calculus, cutting planes, that we've seen actually are used for efficient proof search in practice? We can ask, do they maybe admit automatability? And the answer is no. And this was a breakthrough by Albert Atserias and Müller. And they proved that resolution is not automatable unless NP sits inside P. This is the best result you can hope for. If NP is in P, then resolution is automatable, but if that is not the case, then resolution is not automatable. And this is what we'll cover today. And it turns out it's a beautiful result, and it sort of gives you a pattern for how to prove these results for other proof systems. So this has then been shown for Nordström and polynomial calculus, which is the paper we'll talk about by the Rezende, Goes, myself, Pitassi, Robera, and Sokolov. And we also claim to have a slightly nicer proof of the original theorem than Atserias and Müller had. So that's what we're going to cover today. Whether it is a nicer proof, I guess it's in the eye of the beholder. But so a much more complicated result is the same for cutting planes. Which uses some heavy-duty lifting machinery, somewhat similar to the lifting machinery we have seen in earlier lectures, but with a twist. So it might be within range for us to do this, but it will probably require a few more lectures. Might be really interesting to go over this in a reading group, but not today. And then if you go beyond resolution, you can also get lower bounds for so-called KDNF resolution, where you have not clauses, but KDNF formulas, and resolving is you basically resolve over conjunctions. This is by Godley. All of these are under optimal assumptions, NP not in P. Then we also have non-automatability for tree-like resolution. There, the results by necessity have to be slightly weaker because we actually do know sort of semi-efficient search for tree-like proof systems. And in particular, the results are proven under some version of the exponential time hypothesis, the stronger assumption. This is by Susanna, the Rezende. And there are many more, like there are non-automatability results for subsystems of resolution, and I think some other results that I'm forgetting. And just to make sure that we have time for this, there are some proof systems for which we do not annoy it. Like by now, the picture is clear. We sort of any proof system that is somewhat interesting, we expect it not to be automatable. However, this is open for Shirley-Adams. This is open also for sum of squares. For sum of squares, we will kind of see a little bit why it's open. Shirley-Adams is very annoying, and I should go on record to say that the conference version of this paper, the Rezende et al. Actually claimed non-automatability for Shirley-Adams. This is unfortunately wrong, which you will see in the latest version of the paper that is online. And it seems much harder than we thought. So Shirley-Adams is open, sum of squares is open. Also, you can go to bounded at Frege and above. And you can ask for, now again, when I say that it's open for bounded at Frege, I mean the following. Again, I want it under optimal assumptions. I don't want to assume safe cryptography, just P distinct from NP. And also, I want this for CNF formulas. For bounded depth trigger, you can always play this game of giving formulas that are really, really deep so that bounded depth trigger sort of has no room to start reasoning about them. We don't want to abuse that. We would like to just look at CNF formulas. Okay, so what we're going to talk about today is this result, the original Atserias and Müller, but we'll do it inspired by the Rezende et al. And we'll talk a little bit about what goes into extending this to Nullstellensatz and polynomial calculus, but probably not too much. So the formal theorem that I want to prove, that we will pretty much almost do all of the details for, is okay, so what do we want to prove? Basically, we want to prove that it's NP hard to do efficient proof search. Which means that we're going to take the satisfiability problem and reduce it to a proof search problem. So this theorem that we want to prove, that is theorem 1 in my notes, which is Atserias and Müller, but we're going to prove it as done in the Rezende et al. It says the following. So there exists a polytime algorithm fancy style A, which does the following. You're given a 3 CNF formula, and throughout today, as I said, this formula has n variables. So the algorithm A will take as an input a CNF formula. We don't know whether it's satisfiable or not. We want to decide satisfiability. So it outputs another CNF formula, A of F, which has the following property. So firstly, if F turns out to be satisfiable, if the input formula is satisfiable, then A of F has a short P-refutation. Okay, so P, the proof system P that we're going to work on. So P is going to be resolution or Nullstellensatz or polynomial calculus. For Nullstellensatz and polynomial calculus, we don't really care about the fields. We don't care if you have twin variables, dual variables or not. Like upper bounds will work without it, lower bounds will work with it. So I'll sweep all those details under the rug. So the point is, if F is satisfiable, then there is a short refutation. A of F. However, if F is unsatisfiable, then for AF, we know that it requires P-refutations of length exponential. So exponential in some n to the big omega of 1. And it follows from this a corollary. Suppose we have this, we'll talk about it in a second. The corollary is basically that, well, for such a P, then proof system fancy style P is not automatable. And the corollary is even stronger. I want to stress that the reduction is really tight in the sense that whatever assumption you make about NP carries over. Okay? if you, for instance, say that, so if we say that resolution is automatable in polynomial time, then P is in NP. If you say that resolution is automatable in quasi-polynomial time, so n to the log n to the k, then you place NP in quasi-polynomial time. If resolution is automatable in strictly sub-exponential time, so nx n to the little o 1, then again you place NP in the same complexity class. So I won't write this down, but sort of whatever assumptions you make about NP carry over exactly. So again, whatever assumptions you make for the automatability, however efficient the automatability is, you can solve NP with the same efficiency because of the efficiency of this reduction. So why does this prove? Just as a sanity check, suppose, how do we prove this? Suppose that theorem 1 is true, how do you prove the corollary? Well, you basically say, suppose that resolution, say, admits efficient proof search. Then we'll use that together with this reduction, fancy style A, to solve SAT. How? Well, we know that resolution is automatable, so there is some polynomial running time in which it will find proofs. There are lots of constants around, but basically we know these polynomials. So given a formula with n variables and m clauses, we are making sure that it's a 3CNF. It's kind of convenient. That means that the number of clauses is polynomial in the number of variables. It's a nice property. That's pretty much, I think, all we need. So basically, you just set aside enough time. So you have an automatability algorithm for resolution that runs in some polynomial time. So give it enough time, but set a timeout. So now to decide whether F is satisfiable or not, you take F, you compute the CNF formula A of F, and you run your automatability algorithm. And two things can happen. Either it terminates and finds a short refutation. Well, then we know that we're in case 1, so the original formula F must have been satisfiable. The other possibility is that the algorithm just times out. And now there are two possibilities. It could time out because, in fact, A of F is satisfiable, or it could time out because A of F is unsatisfiable but has a really long proof. In both of these cases, we know that we're in case 2. The only way automatability, the efficient proof search algorithm can have failed is that there was no short proof to find. The only way there can be no short proof to find unsatisfiability of A of F is that F was unsatisfiable. Done. So one thing we can observe about this also that is interesting is keeping with automatability and degree automatability in mind, whatever this formula will be, it will probably require fairly large width or large degree. Because if A of F did admit a narrow proof, then we could just brute force in low width or low degree and find it. So we're looking for a formula that has short proofs, but require a very large degree or very large width. And this is the kind of formulas that we actually do know exist for resolution, for Nullstellensatz, for polynomial calculus. We've seen them. They also exist for Shirley-Adams. We are not able to prove such results currently for sum of squares. We're getting there. There are results in this direction, but you have to fiddle with the encodings a bit. We don't have a clean CNF formula for which you have strong SOS lower bounds, which is sort of, if you prove this lower bound for SOS, then in particular you would find such a formula. So this is sort of a bottleneck for sum of squares. Everything makes sense so far? Okay, so now we are going to describe how this proof goes. So we'll do first like a high-level overview, get the intuition, and then we'll get into more and more details. The details will be somewhat finicky. So I think the important thing is to let's get the intuition right. And the intuition, the important thing is, what does this formula say? What is A of F going to be? This reduction. And the very nice thing is that this is going to be a formula that I'm going to call ref fs. And this formula says, basically, that the input formula F has a resolution refutation in length at most S. Except if we're getting into technical details, at any resolution step, I'll also give you a weakening step for free. But, I mean, it doesn't really matter so much. So basically, ref f of S says, if F has a resolution refutation, it makes the claim that F does have a resolution refutation in small length. Okay? And we're going to fix parameters. It's not, throughout this lecture, S is going to be n raised to the power of 6, where n is the number of variables in F. We'll see why this magic number. We're not going to obsess about it so much. The important thing is S is some polynomial in the number of variables n in the input formula. Okay. So what is this formula going to say? So it has variables in S, I'll call them blocks. What is a block of variables? A block of variables is just a subset of variables. What does each block say? Well, each block just encodes a clause. Okay, so note that, again, the formula says there is a resolution refutation in length at most S, and the formula describes such a proof. So in particular, the formula has variable that describes S clauses. How would you do this? Well, we'll do the data, but it's already clear. I mean, there will be two n indicator variables, for instance, telling you which literals are in the clause, for instance, right? And then, then there will be things like, okay, is this clause an axiom clause? In fact, is it a weakening of an axiom clause? If so, what's the index of that axiom? And then I can, obviously, we know F, so we can check that it is indeed a weakening of, the axiom A sub j, for instance. Or if it is a derived clause, then I'd like to say, can you point me to the two clauses that you resolve to get this clause? So then there are going to be pointer to two earlier blocks. And then there are going to be consistency checks that say that, well, these two blocks should encode clauses. And if I resolve them and possibly do a weakening step, then I get the clause that this block encodes. Is this making some sense? Okay, so the block will encode the clauses plus the local structure of the refutation. And it's hopefully clear we should be able to do this with, a polynomial number of variables. We're going to need something like n log n variables, something like this. Okay. So now for any clause, we define a notion of block width. Let me write this lowercase bv of C. This is for a clause living over the variables in this formula. This is just number of blocks mentioned. And now I don't know about you, but here's where I start to get headaches. So we're going to have to operate at two different levels today. Note that this clause is a clause over the variables in this refutation formula. And the block width of this clause is how many clauses of this supposedly to exist refutation is it mentioning? Okay. So what we are going to do, I need to tell you what this is, what this encoding looks like. But once we have it, we're basically going to say the following: that look at this formula ref fs, and we're going to fix again n to be n raised to the power of 6, where n is the number of variables in this formula f. Then this is a block width, constant block width CNF formula. Why constant block width? Well, it's only going to maintain local information. So the block width, the maximal block width is basically going to be 3 or something like this, because if a block is a derived clause, then I want to know which blocks are you coming from, and we need to be able to verify that. Okay. And okay, this formula should have the following properties: that if F is satisfiable, then there exists a resolution refutation. There exists a resolution refutation of this ref fs formula in length polynomial in the number of variables, and the block width is constant. So I'm claiming that if F is satisfiable, then the claim that F has a refutation is very easy to refute. It's easy to refute the claim that F has a short refutation because it's so obvious that F doesn't have a refutation. I mean, it's satisfiable. However, if F is unsatisfiable, then what we want to prove is that the block width of refuting the claim that F has a short refutation is something like n raised to the power of 4. Except let me put a tilde here because we're going to have some log factors that I'm going to ignore. Okay, so what I need to do now is to tell you what the RefFS formula is, and then we need to argue two things. We need to argue that if F is satisfiable, then this formula will have a short refutation. It will be obvious that the claim that F has a short refutation is false, and the reason that it will be obvious that it's false is that we're in proof complexity, we're not deterministic. Basically, we can just fix a satisfying assignment and use that to guide the proof. And I'll say more about that in 30 seconds. Where we really need to work is in this case, if F is unsatisfiable. Okay. So again, what is the intuition? So for the upper bound, it's convenient to go back to the prosecutor-defendant game that exactly characterizes resolution. I'm looking for a short proof. So I'll just give you an efficient prosecutor strategy. Basically, what does ref f say? It will say something like, locally, the formula is okay. It will say that the final clause is contradiction. That will be hardwired, right? So we'll just, prosecutor will start with the very last block and query the variables in that block. Okay, so actually prosecutor will do two things. Fix a satisfying assignment alpha to the formula f, the original formula f. It has a satisfying assignment alpha, fix one. Okay. Then I'm going to query the final block, and I'm going to convince myself that it is contradiction. Otherwise, prosecutor wins out right there and then. Okay. Now, in particular, alpha violates then contradiction. So now I'm going to walk back in the proof, maintaining the invariant, like I know alpha inside my head as prosecutor, and I will just make sure that I'm walking along clauses violated by alpha. And it's kind of clear that if my current block is a derived clause, and I know alpha is violating that clause, I just need to know, oh, which variable did I resolve over to get here? I identify the two resolvents. One of them had alpha satisfies one of the literals over the resolved variable x and violates the other. So I move to the violated clause. I do some consistency checks to convince myself that alpha is indeed violating this premise. And then I forget everything, and now I just remember this new block. And since premises of resolvents are earlier, I'll keep walking back through the proof. I only remember a constant number of information. Sooner or later, I hit an axiom. When I hit an axiom, I look up what clause is this supposed to be. I'm going to get an index. And then I'm going to verify, well, at this time, I remember that alpha is supposed to violate the clause, but alpha will satisfy the axiom clause. So then I'm going to derive a local contradiction. Turns out you have to be a little bit careful if you want to implement this to keep it small, but sort of at a high level, like if you do naively what I said now, it's actually not quite going to work. You have to be a little bit careful, but this is sort of how it goes. And it's maybe believable that if with some care and remembering exactly the right things, we'll be able to do it. Are you happy with this? So the idea is, again, what are we using? We're really just using that if F is satisfiable, then it's easy to prove that it doesn't have a short refutation. It's easy to prove that regardless of the length, I mean, regardless of S, I will get a proof of size essentially S. I just walk, again, I walk backwards through the proof, walking along violated clauses until I hit the next. In case 2, there are two possible scenarios. If F is unsatisfiable, maybe F, in fact, has a refutation in length S. Maybe F is a super simple formula. Well, then the lower bound kind of vacuously holds, because if F does have a refutation in length less equal S, then this is a satisfiable formula. And for satisfiable formulas, we can prove very strong lower bounds. Kind of a stupid case, but the other case is, okay, suppose that F is not satisfiable, but requires a somewhat long refutation, then it's hard at the meta level to prove that this refutation has to be longer than S. And this is where we will have to work. So in fact, and okay, so this is like, just to stress this, that the whole sort of the breakthrough so far, sort of much of this was known, but here is the breakthrough result, this lower bound. And you can, okay, so one thing I should say that you can, this is just a width lower bound, but in particular, the width is always larger than the block width. And the way we're playing with the parameters here, which you will see later, this width lower bound is actually strong enough to just plug in Bensons-Wigderson. There are also, this is not the way Atserias and Müller did it. They have some kind of a lifting step, which is called, or actually a relativization step, which is a kind of special kind of lifting. We are not going to need that. We're going to play a little bit with the encoding so that once we have this width lower bound, we'll just say, oh, but we learned about Bensons-Wigderson, the size width lower bound long ago. And the way our lower bound goes is actually going to be, and this is, I think it's worth emphasizing this, and maybe we should have talked about it earlier. We're going to do a proof via reductions. And I don't know if you paid attention, but in computational complexity theory, reductions are all over the place, except in proof complexity. Somehow we don't do that many reductions in proof complexity. That is starting to change, in particular, this whole area of total search problems in NP builds heavily on reductions. And to some extent, maybe this particular proof is somewhat inspired by similar techniques. So I think this is also one reason why the lower bound we're going to do is interesting. So in particular, we're going to look at a pigeonhole principle formula for M holes and 2 M pigeons, the so-called retractable pigeonhole principle formula. And it says basically the following. It says that there exists an efficiently invertible mapping that maps 2 M pigeons to M holes. Okay, so it's a weak pigeonhole principle. It's 2 M pigeons that are being sent to M holes, and not only is this possible to do in a one-to-one fashion, but you can even invert this mapping. That's what the formula says. We'll talk about it also in more detail later. So, but basically what we're going to have 2 functions, f, that maps 2 M to M. And then we're going to have a function g that is the inverter, if you like, that maps holes to the pigeons sitting in these holes. How will we encode these functions? Well, we're going to encode them in binary. So for every argument here, there's going to be log n or log m bits that really tells you for every pigeon which hole does it go to. And for every hole, there's going to be log 2m bits that tells you which pigeon is flying here. And now the fact that this is invertible is just the claim. We're going to have clauses that say the following. Well, if it is the case that pigeon I flies into hole J, then it's also the case that when you ask the hole which pigeon is sitting there, then obviously you should answer I. Okay, so these are going to be clauses of basically with 2 log m or something like this. And now what we're going to prove, and this is already from our paper. Is that the block width of refuting the claim that F has a short refutation is the standard width of refuting the RPHP formula. And the only question is how many pigeons and holes will we have? We will have S divided by the number of variables in the formula. So S over N. Okay. So the block width of refuting the claim that F has a short refutation will be at least the width of refuting the retractable weak pigeonhole principle with S over N holes and 2 times S over N pigeons. This is now N to the 5 or something like this, except again, ignoring log factor. And then we're going to use, very happily, that the width of refuting this special pigeonhole principle is linear in the number of holes. And this is by Pavel Pudlak and Neil Tappen. And again, the reason that this is an interesting lower bound is, again, that we make sure that the width of the formula is essentially log m and not n. So this is a non-trivial width lower bound. Okay. And again, once I think I already got ahead of myself and say, okay, suppose that we have this. This means now that if you plug things together, this will give us that the width of refuting ref Fs is going to be at least the block width. And the block width is at least the width of refuting the pigeonhole principle with S over N, which is N5. And I seem to have get a little bit confused now. I think I should have an n squared here probably, because we're going to get, when the dust settles, we're going to get something like n4. I think I'm losing a parameter somewhere in my notes, but we'll see it later. Wait, hang on. Maybe I even have it in my notes. I was just copying incorrectly. Yeah, sorry. We're missing a linear factor right there. So we're losing in this reduction, we're losing a linear factor, but that's fine. And now once we have this lower bound, we can do two things. We can lift this formula, and we've seen before, I think, that when you lift formulas, we saw this for cutting planes, that if you have resolution lower bounds and lift, then you can lift with lower bounds to size lower bounds. And we can get the same thing here, but the lifting is much, much simpler. Or the way we have set our parameters, actually n squared, the number of variables in the formula is going to be something like n to the 7. So n raised to the power of 4 is asymptotically, it's polynomially more than square root total number of variables. So Benson-Wigderson will kick in. And the reason that we can do this is we're actually going to have a slightly different encoding of this formula compared to Atserias and Müller. They basically, when they describe the structure of the resolution refutation, they use indicator variables, which means that we're going to pick up like a polynomial number of variables to describe things. Our pointers back to premises in the resolution rule and so on, we're going to do all our pointers in binary, and that allows us to save variables, and that's why this with lower bound is helpful. Yeah. And for the algebraic version, which I won't really have time to talk about, so let me just say something briefly now. What is the problem? We want to do basically the same. And now you realize that if we can get the same lower bounds, but in terms of degree instead of width, then instead of plugging in Benson-Wigderson, we can just plug in Palazzo-Pudlak-Gall and get a polynomial calculus lower bound. obviously, if I have a size lower bound for polynomial calculus, then I also have a size lower bound for Nordström. Yeah. It does require substantial extra work, but I'm completely cheating you on. All I'm saying is, like, suppose we know that degree lower bounds are much more challenging than width lower bounds, but it's kind of clear that if I can match these parameters with degree instead of width, then the lower bound is fine. The question is, we don't have a prosecutor-defendant game for Nullstellensatz. So will Nullstellensatz actually be able to find a short refutation in the case when F is satisfiable? And we don't know how to do this. So therefore, the formula that we use in this case, which I'm not going to talk about so much except now, it's going to say something slightly stronger. It's going to say that F has a tree-like resolution refutation. And remember, I said before that we give weakenings for free. Now we don't give weakenings for free. We say that weakenings are applied only to the axioms. So basically, you can think of it as you get your formula, you can do one step of weakening, you can weaken your axioms in different directions if you like, and then we're just going to do a tree-like refutation, which means in particular that not only do we know that premises, not only does a resolvent identify its premises uniquely, but both premises identify a single resolvent uniquely. And this somehow helps Nullstellensatz. And then once we have this, we do everything I've sketched so far. So I think what I would like to do now is to start thinking about whether we should have a break. But maybe we're right at the point where before the break, we could talk about exactly what ref fs is, and then we can have the break to just meditate what ref fs is, so that you can digest it, sort of have some time to just think about it. It's not hard in any way, it's just a little bit annoying. Okay, so let's talk about the encoding of this formula ref fs, which again, it's claiming that the three CNF formula f over n variables has a resolution refutation in length at most s, except weakening steps are for free. Okay. So we have S blocks, B1, B2, up to BS. Again, S is going to be n raised to the power of 6, but that's not terribly important. Anything for lifting n raised to the power of 3 would be sufficient for us. And the point is that the block BI just represents or encodes, represents a clause CI that is derived from F. Okay, how would you do this? So every block will have the following variables. Literal indicators, let me call these variables y sub L, for L is in well, x or not x, where x is in the variable set of f. And the idea is just that once I have an assignment to these literals, I know exactly what the clause is. There is an axiom pointer which is, okay, let me say that m is the number of clauses in F. This is getting in a little bit. So m is the number of clauses in F, n is the number of variables. N is the number of variables in F, m is the number of clauses. Since I have a 3CNF formula, they're polynomially related, so log m and log n are going to be the same. Asymptotically. So we have literal indicators. Then we have an axiom pointer. If it so happens that CI is an axiom, the axiom pointer tells me the index of the axiom. And note that we know when we're building this formula exactly what F is. So once it's sort of clear that once you tell me that you're looking at axiom 42, we should be able to hardwire, for instance, exactly what the literal indicator should be, because we know what the axiom clause C42 or A42 is. We also have premise pointers. That's going to be 2 times log s bits. The intended usage of these are, well, if it's a derived clause, then these pointers will identify 2 previous blocks. And let's say that there's an order so that the first block, I mean, I also resolved over a variable. Let's write this out. There's a resolved variable pointer in that case. Resolved variable pointer. How many bits? I guess log m. Let's agree, except if I get this wrong now, I think that let's say that the first pointer is pointing to the clause containing the positive literal over the resolved variable, and the other pointer is pointing to the clause containing the negated literal over the resolved variable. Something like this. I mean, we can agree somehow. Okay, and the only thing I don't know now is, well, what type of clause is it? So I also need like a block type variable. In fact, we're going to have 2 variables for the block type because I need 3 block types. So let's say the block type is tau1, tau2. If tau1 is 1, that's the flag that just says this is a bad block. Please ignore everything in this block. Okay, so you can think of, okay, we'll get to the encoding in a bit, but basically this variable will make sure if tau1 is set to true, then everything in the block should be vacuously satisfied. It's a disabled block. Okay, so this is, if tau1 is 1, this is saying that the type is 1 whatever. And then we have 0, 0, and 0, 1, and then the clause is used. And let's agree that 0, 0 means that we have an axiom clause in this block. 0, 1 means that there is a derived clause in this block. And the idea is that somehow, you know, tau1 and tau2 for the block are going to be carried around in all other constraints, which we're going to talk about in a minute. So for instance, if it isn't an axiom, then sort of vacuously all constraints about the axiom pointer will be satisfied. I sort of use that variable to just switch off those constraints. And again, if we don't have a derived clause, then all of these resolved variable pointer and the premise pointers, we just say, don't worry, like all of these constraints are backwardsly satisfied. How do you do that? Well, you do it basically, you write down the encoding, which we'll talk about in a second. And then if you want to use an activator variable, you just add it. Once you commit it to a clause and encoding, I just add basically to the axiom encoding, I will add then not tau2 everywhere as a literal. So that means that all of these clauses constraining what I mean by an axiom clause are going to switch off and are going to get satisfied because tau2 is going to be false in this case. And similarly for derived clause. Okay? So just let's see what the constraints are, and then we can have a well-deserved break. So what will the constraints be? So firstly, we have so CS, the final clause, has to be enabled. So it's not disabled. Both of these are enabled blocks. And it should be, it should encode bottom. It's an enabled clause. It's a derived clause. And it should be the empty clause. That's how I, so these are the constraints for the block BS, the very final block. Okay, now let's look at other BIs. If we have tau equals 0, 1, then I want to say that CI is a derived clause. Then I say things like the premise pointers, J and J prime, they're both less than I, right? Premises have to come earlier on in the derivation. There's some resolved variable, X. I care about what this variable pointer is. And now I claim that Cj should contain X. Cj prime should contain not X. I claim that if I take Cj union Cj prime and subtract X and X bar, all of these have to appear in Cj, so that Cj is a weakening of the resolvent. And I think this is pretty much it for a derived clause. Everything I care about axiom clauses is switched off. Okay. Okay. If instead we have, we're almost done. So this is derived. If instead we have tau equals 0, 0, then the clause is an axiom clause. Then we get an, I mean, we have an axiom pointer, which is maybe some k, and then we should check consistency with the axiom AK in F, right? I mean, once you know what axiom it is, you're just going to check that all the literals that are there, should be there, are there. In particular, you'll check something like, I think we will want that AK is a subset of CI, for instance. Yeah, that's pretty much it. And then we have finally, if T is disabled, then all of these clauses contains the positive literal tau 1. So once I disable the block, all of these clauses just vanish. Okay. Except where are the clauses? I mean, I'm just sort of giving you a very high level description, but the point is, if you think about this, then the consistency checks with the literals, I think it's pretty clear that those will be binary clauses. Pretty much. Oh, sorry, that's with not binary clauses, but it will be something like, if the pointer is, there's going to be a logarithmic number of bits that says, well, either it isn't axiom 42, or if it is, then here are the literals that have to be there. So that's going to be a logarithmic number of bits, and something like n times log n clauses. And all of these constraints over here, over the pointers, again, all pointers have a logarithmic number of bits. So you can just brute force the encoding, just to do the stupidest thing you could imagine. So since it's over a logarithmic number of variables, we're going to get a polynomial size encoding. And in fact, the reason not to care too much what the encoding is, if you don't like my polynomial size encoding, you can do your polynomial size encoding, and by the completeness of resolution, we can derive your encoding from my encoding. What's the complexity of doing this? Well, you can do it in 2 to the number of variables, and 2 to the logarithmic is polynomial. So I really don't care. I mean, these are once I told you about the variables and that every constraint involved a logarithmic number of variables, then any encoding you like, take it, go with it. And this is going to work because all encodings over a logarithmic number of variables are derivable from one another. Okay, I said we're going to have a break, and we are. I just forgot one thing that I want to add. So in tree ref, what do we need to add to this? We're also going to add a resolvent pointer. Log s bits. Because I know that every clause is used as a resolvent exactly once. And then you're going to add tree likeness constraints that are basically going to say that if Cj and Cj prime were used to derive Ci, then resolvent pointers, the resolvent pointers in Bj and block Bj prime, they should point to I. That's tree likeness. Whenever I look at it, like this clause was used exactly to derive this and nothing else. And again, we still have a logarithmic number of bits, and we're just adding constraints. So tree ref is like a more constrained formula, which makes it easier to refute, makes it harder to prove lower bounds. But this is it. Okay, so now what we need to do is we should have a break. Now that we have our encoding of this formula, unless there are questions about this encoding, we should have a break, meditate over this formula, and when we come back from the break, we are going to talk about how to prove block width lower bounds for refuting this formula under the assumption that F is an unsatisfiable formula. It's also, once we have this encoding in place, you should also think about, okay, how do we implement this efficient prosecutor strategy that actually finds a short refutation? My feeling is we might not get to that. So let me just say right away that actually when you think over how to refute this formula, not only is there going to be a short resolution refutation if F is satisfiable, that refutation is even regular. So going back to one of the first lectures that we have, this means that to refute this formula, you can build a small read-once branching program solving the falsified clause search problem for F, if F is satisfiable. If F is unsatisfiable, then we want to prove a block width lower bound. Okay, let's take a break. So again, our plan is we've fixed the encoding of the ref FS formula, claiming that the 3CNF formula F has a refutation in length of both S. Again, it was really the obvious thing. We just grouped the variables into S blocks, where each block represents a clause and information so that we can check if it is an axiom, which axiom it is, that it is legitimate. If it is a derived clause, if it's a resolvent, I want to know from which clause it was derived by resolution. I want to be able to check that. And the one thing to point out, which I maybe did, but let me do it again, a difference from Atserias and is that we are using our encoding in binary. We're not using the indicator encoding. So you could, for the axiom pointers and the premise pointers, you could have S variables where you just say, is it this block? Is it this block? Is it this block? That would pick up a polynomial number of variables. We're instead just have a single pointer in binary, and that really saves variables for us, which is why we can get away with using Bensazon and Liggerson. Otherwise, it's like, again, the idea, as in all other non-automatability papers that I know, is somehow work with this formula and then follow Atserias and Müller as closely as you can. Kind of. Except the other thing that we're going to talk about that we do differently is we use this retractable pigeonhole principle formula. What variables are there? There are variables fik for I ranging from 1 to 2m, k on log n bits. Jl for j ranging over 1 to m, and l being log 2m bits. The idea is that these fik variables identify a map from all pigeons to the hole they're going to. The g variables identify a whole map for every hole identifying a pigeon. And then the principle states for every I and for every j that if fi is j, then g of j should be I. And this will be a clause of width something like 2 log m plus minus some constants. The number of variables, if I did my math correctly, it's something like m log m variables, and I think m squared log m clauses, something like this. We're going to use this formula heavily. We're also going to use decision trees. So just to recap quickly, suppose I have a decision tree for a Boolean function f. So it queries the variables in f. And let's say it has depth d, so it only queries at most d variables, and then you reach a leaf, which is labeled by 0 or 1, depending on whether f is true or f is false. And querying d variables was enough to decide this. Okay? So suppose for a leaf L, I just write row of L to write the partial assignment that led me exactly to this leaf. For any assignment row, let me write C sub not row to be the clause that are sort of identifying this partial assignment. Namely, it's the maximal clause that is falsified by row. It contains all literals assigned by row but negated. Okay. Then, if I have such a decision tree for a function f, I look at all the leaves labeled 0, and I join together, I add together all the clauses corresponding to the paths to these leaves. Then obviously I get a CNF formula that represents f. And if the tree has depth d, then this is a DCNF formula, just to make sure we're on the same page. Now, the key notion that I want to us to talk about now is, okay, the following. Suppose that x is now a set of variables, x1 up to xn. Y is also a set of variables, y1 up to ym. And f of x and g of y are CNF formulas. So now I want to talk about how to reduce. I want to reduce f to g. So I say that at depth d, decision tree reduction, so f reduces to g via decision tree in depth d. What is that? That is a function from 0, 1 to the n to 0, 1 to the m. Basically, if you give me an assignment to the x variables, I can compute the y variables. That's how we should think about it. Such that every output bit fi, 0, 1 to the n to 0, 1 for I living in M is computable by a decision tree in depth D. Okay, so every coordinate is computable by a depth, somewhat shallow decision tree. Now, take any clause in G and then consider the canonical decision tree that computes C composed with F. Okay, what does this mean? Note that C contains a bunch of literals over the y variables. Composing with F is for every literal, for every variable in turn, let me query the decision tree to figure out what the value of this variable is. If the first variable has a value that already satisfies C, then we're done. Otherwise, query the second variable and figure out the value of that literal. Okay? So clearly this is a depth D times width of C decision tree. Am I making sense? So this is, and the point is that I want that any clause D in the CNF representation, again, I take C, I compose it with F, I get a decision tree of this depth. Now, looking at the CNF representation, this gives me a D times width of C depth decision tree. Look at the 0 leaves in this tree. Expand this out to CNF formula. This is now a CNF formula over the X variables, yes? Okay, any clause in this CNF representation should be a weakening of an axiom in F. If these two properties hold, then I say that F reduces to G via a decision tree of depth D. Are we happy with this? So the reason we care about this, the reason why this is nice is, suppose indeed that F does reduce to G via a decision tree of depth at most D, then what can I say about the width of refuting F in resolution? I'll even tag on the resolution R there for the width, although we're only counting width for resolution today. Well, I claim that this is at most D times the width in resolution of refuting G. And then you know, we have this plus minus 1, so let me throw in just a additive constant. Is the claim clear? So how would we prove this? Well, what we're going to do is we're going to use the prosecutor-defendant game. Okay? In particular, we're going to use the prosecutor-defendant game for G. Basically, we know that the prosecutor, when he's running on G, will be able to ask about this many variables, essentially, and then re-ask and forget and keep going, and eventually is going to land in a winning position violating an axiom. Yes? Okay. So now let's run this strategy, but every time the G prosecutor wants to ask about yi, what do I do? Well, I run the decision tree for fi. I ask about at most d x variables. I get their values. That tells me what y is. Crucially, I remember all of these x variables so that I have fixed the value of y, and then I continue. Okay? So I simulate the strategy of the G prosecutor except with a factor d. Okay? And when the G prosecutor forgets a variable, then obviously I just forget all the variables in the decision tree to compute that variable. Okay? Finally, if not before, we reach a winning position for G. Okay? But that is a clause, we're now violating a clause C. Then it's not so hard to see that, well, in that case, the prosecutor assignment is now violating C composed with F by construction. So it's violating some clause in this CNF representation. So prosecutor is violating some axiom in F, which is a winning position over in this game. Are we? Yes. Okay, good. Perfect. Let me now say that a decision tree reduction, okay, this is a decision tree reduction. So suppose I have a decision tree reduction, which in addition has another property. I'll say that it's block aware. Okay, what is a block aware decision tree reduction? It's a block aware decision tree reduction of depth D is all of this, except a little bit more. So for every block B in the variables of G, so I didn't say this, so the block aware reduction is sort of makes sense if G comes with a block partition. Okay, suppose G comes with a block partition, then we have a block aware reduction. If for every block, when I want to compute, I now want to compute, let me write F block of X. What is this? This is the vector Fi of X for all i's in the block. This is a vector that lives in 0, 1 to the block. This is computed, all of these guys are computed by a depth D decision tree. Let me call it T sub D. Okay? So somehow a single decision tree queries at most D variables in X, and that is sufficient to figure out the whole block. So the leaves of T are labeled with assignments to the whole block. And then I have like, but it's also a standard decision tree reduction like this. Then I claim that, well, okay, let me maybe add just down here that then in fact, if this reduction in that D to G is block aware, then in fact I claim that the width of refuting F is less than D times the block width of refuting G, except for constants. Okay. So again, if the reduction is block aware, then I get the block width measure. Okay, and now basically we're going to be done if we can prove the following.
How does the second condition play with this block awareness?
Good. So take the proof so run exactly the same proof again. So now the point, if you think about the prosecutor-defendant game is really just a characterization of resolution. So now I'm going to use that characterization, but when I measure the memory of the prosecutor, I'm going to measure blocks. Okay, so every prosecutor position, which is a partial assignment row, I'll just count the number of blocks that the prosecutor knows anything about. That is like the block memory of his prosecutor.
In two, like you will replace the width of the class with the block width.
Yeah. So now I'm going to say we just run exactly the same. Like suppose now that G is refutable in some block width. That means that there is a prosecutor that plays and only has position that only knows about that many blocks. Right? So the idea is to somehow to simulate that prosecutor, we're going to ask for every time we mention a new block, I want to know what the variables in this block are. Okay, because there's a single decision tree TB that tells me everything. I just run that decision tree. As soon as the first variable from this block appears, I just query and then I know everything about this block.
So basically you give the defendant all the variables in the block for free as soon as he asks for it first.
Yeah, I don't know if I give the defendant or if I give the prosecutor, but yeah, So as soon as so basically, I'm sort of making the point that I'm making the prosecutor stronger, really, right? You only as soon as you paid for the block, you can have full access to the whole block. And then it's kind of clear that, well, if I have a block-aware reduction, then exactly the same proof goes through. Is that believable? There's really nothing happening. It's just sit down and think about it. And we're really using that. The point that the prosecutor-defendant game is really, it's not like it's not a way of relating resolution to something else. It's like it is resolution. So I can define any width measure I like, and then just adapt. Instead of measuring number of literals in prosecutor memory, use whatever measure you were thinking about. And then you get, for that width measure in resolution, you get the corresponding prosecutor game, where this is the prosecutor memory. Long answer to your question, but it makes sense? Okay, thanks. Except I wanted to. So now I claim that basically all we need to do now is to prove the following. If F is an unsatisfiable CNF formula over n variables, and again I'm setting S to be n raised to the power of 6, then I claim that our PHP with n to the 5 pigeons, 2 times n to the 5 pigeons and n to the 5 holes reduces via decision trees of depth log n, except depth n, but let me throw in, I think, a single log. I think this is n log n, but we can figure this out. Reduces to ref fs via a block aware reduction. Okay. If I can do this, then note that here I have a width lower bound n to the 5. I will lose n log n here, so I will get basically n to the 4 or something. Like, if this is true, then we have our n to the 4 lower bound. Then we should look at this encoding, and now I think I claim that the number of variables here is essentially, what is it? I think it's something like s times n. We maybe pick up a log also. Sorry. No, maybe it's Sm. Okay, which for our setting of parameters is n to the 7. And the point is that here we're going to get n to the 4, give or take, which is more than the square root of n to the 7. So if we can, well, we also didn't go over the details of the upper bound, except we sort of talked about it. And maybe you're convinced that this is not the hard part, at least not for resolution. Nullstellensatz is another story. So if we can prove this, then we're essentially done. This is all we need to do. Okay. So why would this at all be related? So basically what I'm going to do is the following. Let me do it by picture. Let us consider the canonical tree-like refutation of size of length 2 to the n plus 1 minus 1. Okay, which is just a complete binary tree, and it starts at bottom layer, it resolves xn everywhere. Next layer resolves away xn minus 1 everywhere, and at the top layer it resolves away x2 everywhere and then x1 everywhere. Okay, we're going to think of this proof being embedded. Okay, so I'm going to embed this proof in S n to the 6 blocks process. So we're going to do the ever so slightly compress the proof a little bit. We're going to compress this exponentially large proof into n to the 6 clauses. That's our idea. How are we going to do this? There are going to be layers What am I going to call the layers? The layers of blocks L0, L1, L2, up to L1. The number of blocks in L1, in Li, is going to be, so I need n blocks, and I only have S to be n6. So I can afford like n to the 5 blocks per layer, but the very early blocks are not going to need that much. So I take the min of 2 to the I and n5. Okay, so let's start by drawing a picture. So basically, I'm going to think about this as, here's the top layer. Now I want to cheat here. I prepared a picture, which is the same picture that we have in the paper. So the idea is somehow in the beginning, I will just, I can afford to actually build a full resolution proof. So going a little bit ahead of ourselves, like when I can actually represent the full layers, I could actually imagine just hard coding. So let me write what I can do here. So I'm going to think about this as this is actually bottom. This is x1. Let me think of this as not x1. Let me skip the ors just to have less typing. Is that fine with you? Then this is the clause x1, x2. This is the clause x1, not x2. This will be not x1, x2. This will be not x1, not x2. So for a while, I'm just going to, and basically what we're going to do here, we're getting a little bit ahead of ourselves, but this is BS. This is like BS minus 1, BS minus 2, BS minus 3, 4, 5, 6. These I'm just going to hard code. Right? I can, for these blocks, there's going to be like the decision tree is going to have a single node which just says, oh, you're looking at block BS. Well, let me tell you what BS is. It's exactly this. But now suppose I hit the limit here. So S over N is 4, apparently, in this picture. Now, what do I know? Well, in these layers, I know the following. That in every layer here, I have, this is a clause. This is maybe, I think this will be a resolvent or something. So it has 2 premises. This guy also has 2 premises. This has 2 premises, 2 premises. Right? Am I making sense? And the point is, what do I know about these premise pointers? Well, we can agree that I'm going to point down just to the next layer. But now we have a little bit of a problem because we have S over N nodes here. We have S over N nodes here. And we need, let me fix that to be a layer length capital L maybe. It's actually going to be N to the 5. So we have like 2 times N to the 5 pointers here that are pointing down to just N to the 5 guys here. So the way we're going to think about this now is that the premises are the pigeons, and they are identifying these guys. And now it's sort of clear, maybe, where the pigeonhole principle comes in. So we have the weak pigeonhole principle saying, no, that's fine. I do have a mapping from these 2 times N to the 5 pigeons to these N to the 5 holes. And it is a perfectly one-to-one mapping. It's invertible. It's everything. Right? And the point is that resolution will have a hard time figuring out that we're lying. So we're just basically, we're going to, between the layers now, we're going to set things up so that basically the mapping from one layer down to the next is the pigeonhole principle. Okay. So what will this look like? So let me try to draw a cute picture. So we will have now, basically in this case, we want the pigeonhole principle mapping 8 pigeons to 4 holes, right? So suppose here it is. So this is like the RPHP. And now suppose I give you a concrete truth value assignment. And now we're running out of space. Maybe I'll keep the encoding. Do we remember what a decision tree reduction is so that it's block aware? Like maybe I'll get rid of this for now, or maybe both this and the other book. So I hope that intuitively it's making some kind of sense, but what does this actually mean? We need to make the reduction, we need to make it block aware. Suppose, just for simplicity, let me define the following. So look at the RPHP variables. So basically, we're actually gonna use the same formula everywhere. And let me tell you how. So when we have the RPHP, suppose for now, like for simplicity, suppose that I actually get a complete assignment to these variables. Okay? Just mentally in our heads to see what's going on. Suppose I have a complete assignment to this. Let me define a partial mapping of pigeons to holes in the following way. H of I is going to be F of I, where F is this guy. If indeed, if I take F of I send it over to some J, and I invert it, I get I back. Then I'm happy. Okay? Otherwise, H of I is undefined. Okay, so basically, and now my idea is now that given any truth value assignment to the F and the G's, this defines a partial mapping. If we actually, and it's going to be a partial matching, it's going to be efficiently invertible. Obviously, if we get a star, we're going to be in trouble. But you know, let's not worry about it too much. Suppose that I have an assignment that looks something like this. So now again we have these 8 pigeons and these 4 holes. So looking at this picture, I will think of this as the premise clauses, and these are the clauses one layer above. Right, so these are now, these orange guys are here. And suppose I get a complete truth value assignment. And suppose when I look at HI, I get that this guy is hooked up, this pigeon is hooked up with this hole, and they agree, the pigeon and the hole. This pigeon and this hole agrees. This pigeon and this hole agrees. There are no other agreements. Okay, so in particular, H of this guy, H of this guy, this guy, this guy, this guy, they're just stars. They're undefined. Then what I want to think about is I'm going to copy I'm going to view these as resolution edges now, and I'm just going to copy them, if I can do so, in between all of these layers. Let's see if I can do this. So I'm going to say that this is one of the resolvents here. This clause and this clause were resolved to get this guy. Same thing one layer below. And we just keep going. Now, obviously, how the defendant is going to play on this graph might be highly adaptive, and we forget things and then get other assignments. But at all times, any assignment to these variables will define something like this. And then it will be, we will sort of make sure that our decision tree reduction interprets this as this. Okay? And now the only question is, like, what does this mean? So again, until we hit, as long as we can afford to embed the whole decision tree, here we're just going to hard code. And in particular, in that part, this will be a locally set. I mean, this is a perfectly fine tree-like resolution refutation. So this is going to be perfectly fine. Now I'm going to look at these arrows, and here's an observation. Like, I know we have agreed how to use RPHP to get these arrows. So in particular, if I'm wondering, for this block over here, what is it resolved to be? Okay. And the answer is just, I say, okay, this is block 2. So I will query to get G of 2. That gives me some guy over here. Apparently G of 2 gives me 2. Okay. Now I query F of 2. And if F of 2 is also 2, then I know that this is an edge. So note that so I can find this arrow, if it exists, with just 2 log n queries. What would I do if I query this guy and it says 2 and then F of 2 is 5? Then we just say, okay, then this edge didn't exist. That's exactly what happens. Maybe here I query, maybe here I actually queried G of 4 and I got 3, and then F of 3 unfortunately was 1, then I don't have a matching here, right? Then this condition fails. Actually here in this direction, the point is I can compute both H and H inverse. Is this making some sense? So then, intuitively, what I want to happen, and we'll set up the decision tree in a second, but sort of now I know what I'm thinking about. Again, here it's easy to see that what should be the variable. I know what layer I'm in. This is layer, this was layer 0, 1, 2. This is layer 3. So clearly I'm resolving x3 here. And I know that these two guys are pointing there. So they contain, both of them contain x1, not x2. Okay, maybe that isn't such a great color. Maybe I'll keep going with blue. This contains x1, not x2. This also contains x1, not x2. And then they should resolve over x3. The left guy contains x3 positively. The right guy contains x3 negatively. Okay. What should this clause be? Well, it contains x1, x2. And then it's apparently the left resolvent, so it must be not x3. What do I get down here? Well, here, these are apparently x1, x2, not x3, x1, x2, not x3. And then at this layer, I'm resolving x4. This is the one that contains x4 positively. This is the guy that contains x4 negatively. Same here, this must be x1 not x2, x3 not x4. And just to see if I'm getting this right, again, this is then x1 not x2, x3 not x4, x5, x3 not x2, x3 not x4, not x5. And this one has to be x1, x2, not x3, x4, not x5. Supposing that this is the fixed assignment. But the point is, how will I figure out these arrows? I'm going to query the variables of RPHP. Okay. What should I do with these guys? So if I start querying these guys, I apparently don't find any resolvents. And then let me just decide, okay, then this is a bad block. Let me disable it. Oh, one thing that I also didn't say, another thing, like clearly this will not be, here I'm using up my N5 blocks per layer, but I'm not using up all N6 because the final layers are using less, right? So there will be some blocks left over also. Let me disable them also. So there are like a bunch of blocks down here also. And all of them are just, I'm not using them. Okay, so I use as many blocks I need for this structure and then disable the rest. And then the intuition is that whenever I query and I don't get a pointer, then I will also consider the block to be disabled. Okay, and the question is now, but what does this mean? How do we do this formally? And let's just go over this. So let's see what the decision tree reduction is. Consider the jth block in ith layer, Li. The jth block, let's maybe call it Bj, maybe with a raised to the power of I. I don't think I'm going to use this. Okay. So what I want to do now, I want to query all of these variables with big O of n log n bits to these variables. Okay, note that just querying a single value is actually just a logarithmic number of bits, but I have n log n bits because I'm going to query more than just like a single pigeonhole pair. So, okay, so what do I need? Let's look at the, let's do the premise pointers first. So the important thing is to note that I know what J is and I know what I is. My notes are a little bit messed up here, by the way, if you're reading my notes. I can actually compute I and J also, but I don't need to do that. I know what this block is, and I know in my head that this is the layout we have in mind. So if you give me a particular block B42, I know exactly where it is in the structure. Okay? So B42 is in fact the jth block in the ith layer. So maybe do the easy things, for instance. Let the axiom, so like axiom pointer. Well, I only need to do this if I is equal to n. And if so, how do I do it? Let's get there. It's a little bit complicated. The premise pointers, that's easier. Well, if I only need premise pointers if I is strictly less than n. And then what are my premise pointers? Well, they're just going to be, let's agree that the premise pointers are h2j minus 1 and h2j, where h is this guy. Okay, so clearly this, how many bits are these? Just the logarithmic number of bits, right? Are we happy so far? And whether I'm an axiom or not, that I even don't need to query because I know where I am. Which axiom I am? That's a little bit tricky. So here comes a more delicate thing. Literal indicators. How do I know which literal I contain? Like in particular, suppose we're looking at this guy. And apparently you and I did the picture, and apparently we should have literals x1, not x2, x3, and not x4. How do we know this? So here's what I'm going to do. We already said that I can query hi, but I can also invert it, right? By, if I know j, then I just compute g of j, which gives me a potential I value, and then I compute f of y and see if I get it back. Then I know both hi and hj inverse, and they're the same. Otherwise, if the back and forth fail, then I have a star. Should I be worried about the star? Yes and no. The point is, note that if I ever see a star, then I'm actually violating an RPHP axiom, which means I'm in good shape. That means that sort of, if I'm ever violating an RPHP axiom, well, then we sort of won already, and presumably the defendant over here is going to make sure that doesn't happen. Like I know it's hard to win against RPHP. Okay. So for literal indicators, I'm going to compute the inverse of h repeatedly to get path leading to some sink. To some sink, let me call it, I reached the sink in block B tau. That's actually a bad, tau is occupied, maybe B sigma is my sink. Okay. Now there are two cases. Suppose that case one, B sigma is not BS. Okay, when could that happen? Well, for instance, here, for instance, it immediately happens, right? Okay, so I start, figuring out what are the literals here. And then I just say, well, then I make B, I, J disabled. And then I can fix all variables in the block to whatever I like. Then we can just agree, let's set all variables to false. I don't care. I just disable the block. Okay. Case two, this case two is what happens here. I go left, right, left, right. And now the decision tree actually figures out that it hit, now it knows that it hit the final block at level 0, right? We know this. Okay, so B sigma is BS. Then I will trace path backwards. And basically what's going to happen is when I trace the path backwards is whenever I go left, that gives me an xi. Whenever I go right, this gives me a not xi, where I is the right literal, right? So here, let's see what happens. I go left, right, left, right. And going back, I first go left, so x1 is positive. Then I go right, so x2 is negative. I go left, x3 is positive. I go right, x4 is negative. Okay, so now I know exactly that these are the literals in this clause. What's the depth of this? N times log n. Worst case. Right? So something like O n log n queries. But now, okay, fantastic. Let's see, let's continue. The resolved variable pointer. Well, that is decided by layer. I guess at layer I, it's going to be, it's xi plus 1, I guess I'm screwing up, right? We're here in layer 1, 0, 1, 2, 3, 4. I know that the resolved variables is x5, just by virtue of the block lying here. Okay, so I don't need to query to get this. What about the axiom pointer? Well, if I'm down here, so at level I equals n, I have a clause with m over all variables, right? And I know I've computed what this clause is, and now we know what f is. So you and I can just agree, for all 2 to the m clauses, just fix a violated axiom, and that's going to be, so just we fix an aj in f ahead of time, right? And now the block type is going to be the following. The block is going to be disabled if something goes wrong. What is it that can go wrong? I guess I can fail to actually, but the way I've drawn it here is I didn't disable this block. So I guess if something goes wrong with the literals, I guess, then I give up. I don't know. I could disable, I guess, if something happens with the premise pointers, but my picture here didn't do that. So let me actually not do that. Okay, but otherwise, it's derived if layer I is less than n. It's an axiom if I is equal to n. I claim that this reduction uses, I think that it uses big O of n log n queries. And that computes all variables in Bij, hence it is block aware. Are you buying this? I mean, I made sure that it's block aware. The only question is, yeah, but is it a reduction? Okay, maybe I'll work over here. one thing I didn't, or did I? Yes, I did say this. Okay, so now again, what is the reduction? These guys are all hard-coded. So these are decision trees of depth 0, where I just say, okay, I know exactly what this is. Just given the index, this is what the clause should be. So this is the hard-coded part. And it's kind of obvious that no problem could possibly arise over there. I'm not going to see any violations. And this part is where I repeatedly use RPHP. And okay, so what are my constraints? Okay, brilliant. I just erased them. That's great. That's my board technique to maintain plausible deniability. So let's see, what did we have? Well, I claim that for the, okay, so firstly, I only need to worry about enabled block. Disabled blocks were off the hook. For enabled blocks, I claim that the literals are always going to be fine. They're always going to be consistent if I have these arrows. Okay, so check for the literal indicators. The axiom pointers are going to be fine if I actually identify an axiom down here. Then, I mean, we just defined whatever the weakened clause is, we'll define it to agree with an axiom. The result variable pointer, that's fine. I mean, that's defined by the layer, so not a problem there. The block type is also fine, I claim, but I'm sort of trying to zoom in on what could possibly give us problems. And what could give us problems is the premise pointers. In particular, like in particular, if someone starts hitting this block really hard and wants to know what this premise is. Okay. Suppose someone hits this premise pointer really hard and figures out that actually age of 1 is apparently star. That is a problem. So our problem is, what if the only problem I claim, we want to finish now, so I'm speeding up a little bit. The problem is, what if age 2 to the j minus 1 or age of 2j is equal to star? That's the one thing that can go wrong. Because then I have a violation here. But the point is that, yeah, but if H is star, then we have found a violated axiom here. So we're claiming that if I find, like, what are the axioms that could be violated? The violated axioms could be the axioms that talk about premise pointers and how they are set up. But whenever I find such a violated clause, I've also violated an RPHP clause. So then we're claiming that that yes, we have a violation here, but it's implied by this violation. I think it's time to wrap up, maybe. Let me just say something about the upper bound. Which we can do for regular resolution. Which means we can do it for a read once branching program, capital Pi. And basically, the read once branching programs are going to have main nodes, VI. And I'm just going to walk from, and then we can talk about how to connect these guys. But basically, what VI is going to say is something like, it's going to say something like the following. VI is an enabled block. We're going to, again, we're going to fix an alpha satisfying F. Let me write alpha as the literal set to true, L1, L2, up to Ln. Okay, alpha contains Ln pairwise distinct literals, the literal set to true. Fix alpha. Then I'm going to have S main nodes, where S is the number of clauses in the purported resolution reputation. And whenever the branching program reaches node VI, it knows that BI is enabled. And it also knows that BI encodes a clause not containing any Li for I in M. No literal set to true by alpha. Okay, and now basically what we just need to do is, okay, in the setup phase, we start by querying everything about the block BS. What do we know about that block? Well, we have axioms claiming that this block is enabled. It's contradiction, which in particular means that it doesn't contain any literals Li. If this isn't true, then we have one already, right? We identified, we have some violation of the block axioms for BS. Okay, otherwise, let's suppose now, so otherwise we are at V sub S. Okay, so by induction, suppose we are at V sub I, then what am I going to do? Firstly, I query, what's the type of this axiom? I already know that it's type of this clause, type of this block. I know it's enabled. So I check if it's an axiom. Well, if it is an axiom, it's kind of clear what I should do. Just ask about the index, and I get an axiom index. And now we're in good shape, right? Because that axiom is satisfied by alpha, so it definitely contains an Li. So I'm going to find the contradiction. I mean, so VI knows that this clause wasn't supposed to contain any satisfied literal, but now it's a super clause of some axiom that definitely does contain a satisfied literal. So we're going to hit a contradiction and the branching program wins. Okay. Otherwise, if it's a derived clause, well, then there are premises. So we query to get the premises. We check that both premise clauses are earlier. We know now, in fact, we know also which one of the premise clauses. We check what the resolved variable is. Once we get that variable, we know we pick the literal that alpha falsifies. We move to that premise clause. So let's say that's VJ. And now we do a lot of consistency checks. We check that indeed we know already that we know what clauses BI was encoding, and we know that it's a superset of the clauses in encoded by BJ, except for this literal over X, but it is falsified. So we just query, and if everything is consistent, we can finally move on to VJ. If everything is not consistent, then we won in the transition. So we just keep going. This is basically the proof, and this is going to be what's the size of the branching program? The size of the branching program is something like S times some logarithmics and probably some linear factors, and this is it. And again, if we want to, again, what is the problem if we want to do this for algebraic proof systems? We need to define not a decision tree reduction, but we need an algebraic low degree reduction. It's kind of going to be the same, except that these functions f are going to have the property that when you look at the polynomial representation, it's going to be derivable in low degree in Nordström. Then you can run the same kind of reduction, assuming that you can get an RPHP lower bound, degree lower bound, which you can. Then you again get a degree lower bound in polynomial calculus. You do Paleophil-Pascal, you're done. For the upper bound, what we just sketched over here gets more complicated, and you're going to use that. You can sort of do local consistency checks and remember things. And really, since you're tree-like, there are premise pointers and resolvent pointers, and you can like do local checks. That makes life for Nordström much easier. We also have non-automatability results for cutting planes. Again, they require heavy-duty lifting, much more complicated. It's open for Shirley-Adams, sum of squares, and for optimal assumptions bounded at Frege. One thing that I hope we'll talk about later this semester is a follow-up work by Noel, Arteche, Susanna de Rezende, Atserias, and I'm blanking on the names there, Farkaniki also, probably. That basically, what we show now is that, okay, if I know a satisfying assignment, then I can get a short refutation. You can sort of ask the philosophical question, is there any other way of refuting this formula? Or if I just give you a resolution refutation of this formula, can you actually decode a satisfying assignment of F? Like if I give you a short refutation of Fs, can you actually read off a satisfying assignment alpha? And essentially, this is what they prove that yes, which has some fairly intriguing consequences. I hope we'll have a separate seminar about this. But this, I think, is what I wanted to say today. Any final questions before we wrap up? So then let us call it today.